Look at your hand. Right now. The atoms in your fingernails, the molecules in your skin cells, the electrons moving through your nerves, every single particle in your body, and I mean every single one, is doing something that, when you actually understand what's happening, will make you question whether the word real means what you thought it meant. I'm not going to ease into this. The most unsettling truth, quantum physics revealed, isn't that particles can be in two places at once, or that observation affects reality, or any of that mystical nonsense people love to repeat. It's simpler and far more disturbing. Nothing has definite properties until it interacts with something else. Not we don't know what properties it has. Not we can't measure the properties without disturbing them. The particle doesn't have those properties. Period. No hidden values waiting to be discovered. The electron doesn't have a position. It doesn't have a momentum. It doesn't have a spin direction. These things literally do not exist until the electron interacts with something. And before you think I'm playing word games or diving into philosophy, I'm not. This is measurable. We can test it. And every single test for nearly a century now confirms this same bizarre picture. Here's where it starts to get concrete. Take an electron. Simple enough. Basic particle, negative charge. Incredibly light. Now ask, where is it? You might think that's a reasonable question. After all, the electron exists, right? It's somewhere. Even if we can't measure its position without disturbing it, surely it has a position. There's a fact of the matter about where the electron is, even if we don't know it. Wrong. In 1927, Werner Heisenberg figured out something fundamental. If you try to measure where an electron is very precisely, you lose all information about how fast it's moving. If you measure its speed precisely, you lose all information about its position. And here's the key. This isn't a limitation of our instruments. The electron genuinely doesn't have both a precise location and a precise speed at the same time. Not because we're clumsy experimenters. Because reality at this scale doesn't work that way. How do we know this isn't just about measurement problems? Because if electrons had all their properties predetermined, just hidden from us, then certain patterns would show up in experiments. In 1964, a physicist named John Bell figured out exactly what those patterns would look like. He worked out specific limits that any hidden property theory would have to obey. Then we tested it, starting in the 1980s with Alan Aspect's experiments, and hundreds of times since. The results? Those limits are broken, violated, exceeded. Every single time. The properties aren't hidden. They don't exist until measured. Let me show you what this actually means with a real experiment. Take two electrons and prepare them in a special way so their properties are connected. We call this entanglement. Now separate them. Put one electron in a lab in Paris. Put the other in Tokyo, thousands of miles apart. Here's what happens. You measure a property of the Paris electron. Let's say its spin, which can be either up or down when you measure it. You choose to measure along the vertical direction. You get a result. Spin up. Random. 50-50 chance it could have been down. But here's the strange part. The instant, and I mean instant, you make that measurement in Paris, the Tokyo electron now has a definite spin too. Measure it along the same vertical direction and you'll get spin down. Every single time. Perfect correlation. Wait, you say. Maybe the spins were determined when the electrons were created. One was always up, one was always down. We just didn't know which until we measured. That's exactly what Einstein thought in 1935. It's the obvious explanation. It's wrong. Here's why. You didn't have to measure the Paris electron vertically. You could have measured it horizontally instead, left or right, and you'd get a result. And the Tokyo electron would instantly have the opposite horizontal spin. Or you could measure at a 45-degree angle, or any angle you choose. Whatever measurement direction you pick in Paris instantly determines what the Tokyo electron will show when measured. But here's the critical point. You don't decide which direction to measure until after the electrons are separated. The Tokyo electron can't know in advance which measurement you'll choose, so it can't have predetermined answers for all possible measurements stored inside it somehow. John Bell proved this with mathematics. If the electrons carried hidden instructions for every possible measurement, the correlations we'd see would be limited. They'd be weaker. But what we actually measure, the correlations are stronger, much stronger, too strong for any hidden instruction theory to explain. The universe doesn't have an answer to what is the Tokyo electron's spin until you measure the Paris electron. The measurement in Paris, your choice of which property to measure, determines what properties exist in Tokyo. This isn't interpretation. This isn't philosophy debating how many angels dance on a pin. This is what the mathematics requires and what every experiment confirms. Now let's make this worse. Because it's not just electrons in carefully controlled lab experiments, it's everything. Every particle, every atom, every molecule in the universe exists in this state of indefinite properties until interactions force them to become definite. You're sitting there reading this. You feel solid. Your chair feels solid. The atoms making up your body, the electrons in those atoms don't have definite positions. They're not tiny balls sitting at specific locations orbiting the nucleus. They exist as a cloud of possibilities spread out around the nucleus. That electron isn't hiding somewhere in that cloud. It genuinely is the entire cloud. All of it. Simultaneously. The electron doesn't have a single location. It has many potential locations at once. Only when something interacts with it, another particle, a photon, anything, does it suddenly have one specific location. When does that happen? When there's an interaction that leaves a permanent record, when the electron hits a detector, when it bounces off another atom in a way that can't be undone, when it exchanges energy with something else in a way that amplifies from the quantum scale to something larger. This is where quantum mechanics gets genuinely unsettling. We don't completely understand where the boundary is. Small systems, single electrons, individual atoms, even some larger molecules definitely exist in this state of multiple possibilities at once. We've measured it directly. Large systems, tables, chairs, cats, people definitely don't. They have definite properties at any given moment. Somewhere between a few atoms and a few trillion atoms, this multiplicity of possibilities becomes impossible to maintain. The system interacts with too many other things. Photons bouncing off it, air molecules hitting it, vibrations from nearby objects. These countless interactions constantly force properties to become definite. This process is called decoherence. For anything bigger than a speck of dust floating in air, it happens almost instantly. Faster than you can blink, faster than you can think, unimaginably fast. But decoherence doesn't solve the fundamental mystery. It just explains why big things look definite. At some point, real definite outcomes emerge from the quantum possibilities. We call this measurement or observation, but those are terrible words that confuse everyone. It's not about consciousness. It's not about humans looking at things. A rock can measure an electron. A grain of sand can observe an atom. It's about physical interactions that create permanent, irreversible records. Where exactly does indefiniteness become definiteness? We still don't know. That's called the measurement problem. 90 years after quantum mechanics was developed, we still don't have complete agreement on how definite reality emerges from indefinite possibilities. Some physicists say the universe splits, every possibility becomes real in its own separate universe. That's the many worlds interpretation. Some say consciousness matters. That's mostly nonsense. Some say there's a spontaneous collapse mechanism we haven't discovered yet. Some say we're asking the wrong question entirely. Here's what I know for certain. The mathematics works. Quantum mechanics is the most precisely tested theory in the history of physics. Every prediction it makes about what we'll measure comes out correct, sometimes to an absurd level of precision, 15 decimal places in some cases. And what quantum mechanics tells us is this: reality at the fundamental level isn't made of things with definite properties existing independently. It's made of possibilities that crystallize into actualities through interaction. Think about what this means. The universe at its foundation isn't a collection of objects with properties moving around in space and time. It's a web of interactions. Each interaction creates definite results from indefinite possibilities. Each result becomes the starting point for new interactions. Before you measure the Paris electron, neither electron has a definite spin in any direction. The measurement doesn't reveal something that was already there. It creates that property, and simultaneously creates the correlated property in Tokyo. This isn't spooky action at a distance. Einstein's dismissive phrase for it. Nothing travels between Paris and Tokyo. No signal. No information that could be used to send a message. What's happening is stranger than that. The two electrons were never really separate to begin with. They're one system. One thing, not two things. Measuring one part of that unified system determines properties throughout the entire system. Not because signals travel between parts, but because parts isn't the right way to think about it. Space doesn't separate quantum systems the way it separates marbles in a bag. Entangled particles remain one unified entity, no matter how far apart they are. The whole idea of separate objects with independent properties breaks down. This has real consequences. We're building quantum computers right now that exploit this. They work by putting quantum bits into genuine superposition, actually being 0 and 1 simultaneously. Not just we don't know which, and letting them interfere with each other in ways that regular computer bits can't. We're developing quantum cryptography that's fundamentally unbreakable because any eavesdropping forces the quantum system into definite states and destroys the interference patterns, revealing the intrusion. We've done experiments putting molecules containing over 2,000 atoms into superposition, molecules you could almost see under a good microscope. We've demonstrated quantum entanglement with objects visible to the naked eye, tiny mechanical oscillators that are entangled with each other. We've measured quantum effects in biological systems. Birds apparently use quantum entanglement in their eyes for navigation. The quantum world isn't some separate bizarre realm disconnected from everyday life. It's the foundation. Everything is quantum. The classical world you experience, objects with definite positions and speeds, emerges from quantum mechanics through continuous interaction with the environment. But underneath everything, all the way down, it's quantum. Everything exists in superposition until interaction pins things down. So when I say look at your hand, what are you really looking at? A collection of atoms sitting at definite positions? No. Each atom is a cloud of quantum possibilities. Electrons don't orbit the nucleus like planets around the sun. They exist as probability clouds. Those electrons only have definite properties in relation to each other, through constant interaction. The solidity you feel when you touch something isn't particles making contact like billiard balls. It's electromagnetic forces, electrons in your hand repelling electrons in the object through quantum field interactions. Even that force emerges from quantum processes involving the exchange of virtual photons. Nothing is classical at the bottom. You're not a thing. You're a process, a pattern of interactions. Each interaction creates local definiteness from fundamental indefiniteness. Every moment, countless interactions are pinning down properties that didn't exist a microsecond earlier. And those properties become indefinite again immediately after, until the next interaction defines them. Does this mean reality is subjective? No. Measurements give definite, reproducible results. Everyone who measures that electron in Paris gets the same answer. The properties become real through interaction, but they're real in relation to whatever they interact with. Not real in some absolute sense, floating out there, independent of everything else. This is what quantum mechanics revealed about reality. Not that it's weird in some mystical New Age way. Not that consciousness creates reality, or you can manifest things by thinking about them. But that the properties we think of as fundamental, position, speed, spin, energy, all of it, only exist in relation to other systems through interaction. The universe at its foundation isn't made of stuff with built-in properties. It's made of relationships. Properties emerge from interactions between systems. Before interaction, asking what properties does this particle have has no answer. Not because we're ignorant, not because the answer is hidden from us, because there is no fact of the matter. The question itself is wrong. That's the unsettling truth. Reality is relational, not absolute. Properties don't exist independently. They exist between things, created through interaction. And once you understand this, really understand it, you can't go back to the old way of thinking. You can't see objects as having definite properties on their own, independent of everything else. The world stops being a collection of things and becomes a network of interactions, creating temporary definiteness from fundamental indefiniteness. Every time something interacts with something else, every time you touch something, look at something, measure something, you're not discovering what was already there, waiting to be found. You're participating in creating what becomes definite in that moment, not through consciousness or magic or wishful thinking, through ordinary physical interaction that forces quantum systems to take on specific values. This is what we know. This is what decades of experiments tell us. This is what the mathematics of quantum mechanics requires. We still don't fully understand why reality works this way. We don't know where quantum indefiniteness ends and classical definiteness begins. We don't know what makes the difference between possibilities and actualities. But we know it works this way. Every test confirms it. Every prediction comes true. Quantum mechanics is the most successful scientific theory ever created. And what it tells us about reality is strange beyond anything philosophers or scientists imagined before 1925. That's the world you live in. That's what your hand is made of. That's what everything is made of. Not particles with properties, but possibilities that become actualities through interaction. Reality is not what it appears to be, not even close.